Okay, hi everyone. I think I'll get started. My connection has been spotty today, so if I drop offline, give me at least a couple of minutes, I might come back. And also let me know if something glitches and you miss something in the chat or something something I said didn't come through. I mean, just be more. Don't be shy to let me know if something isn't clear, or particularly for tech reasons, but more generally. Okay, so we're going to just finish our crash course on branching processes and then move on to random graphs. So I'll spend a few lectures talking about the Erdős-Rényi random graph and component sizes in Erdős-Rényi random graphs. Today, that discussion will principally be using very, let's say, naive approaches, just sort of following our nose and seeing what we get to start by computing expected values. And then we'll see how much more we can get by comparison with the branching process. And then tomorrow we'll start to prove laws of large numbers, so to understand first order statistics of component sizes in a bit more detail. Today we'll only see bounds rather than precise asymptotic values. So that's where we're headed. Let me just start by recalling some of the things we did last class. So last lecture we saw branching processes. We saw the cycle lemma, and we did this case study, which was Poisson branching, in which case we saw that the probability, so for T Poisson 1 branching process, the probability that the size of T is n is n to the n minus 1 e to the minus n over n factorial, which was in particular sort of roughly 1 over n to the 3/2. Okay, so I just like to, because it's going to be useful for intuition and it's easy to say right now, mention what happens when we have a Poisson branching process with mean just slightly less than 1. So let's fix some parameter epsilon small and let T be Poisson 1 minus epsilon in MHE. Then what do we get out of the cycle lemma? We get, so the probability that T has size m is 1 over m times the probability that a Poisson random variable with mean 1 minus epsilon m is m minus 1. Okay, so that's 1 on m, and now 1 minus epsilon m to the m minus 1 e to the minus 1 minus epsilon m on m minus 1 factorial. And if you use Stirling's formula in this case, you get that this is roughly order 1 on m to the 3/2, but now there's a correction term, which is 1 minus epsilon e to the epsilon to the m. Okay, so you get a 1 minus epsilon to the m from here, and then an e to the epsilon out of this exponential. Okay, and so this you can check that this is at most 1 minus epsilon squared on 2, and so this is like at most order 1 on m to the 3/2, and then e to the minus epsilon squared m on 2. Okay, and so if you, if m is much smaller than 1 over epsilon squared, this just looks like the same sort of bound we were getting for critical trees. But once m is much bigger than 1 on epsilon squared, then we start to get a sort of exponential penalization. So these trees, that says that that a subcritical tree looks roughly like a critical tree, or the probability of observing trees of a given size is roughly the same until about m is 1 on epsilon squared, and then it drops off. And so in particular, if we look at the probability that that this now Poisson 1 minus epsilon BNMA tree has size bigger than x on epsilon squared, then this is, roughly just, so I'm going to multiply and divide by epsilon cubed so that I can write this as epsilon squared m to the 3/2 e to the minus epsilon squared m on 2. Okay, so I'm just summing this bound over m at least x on epsilon squared, and I've introduced this multiplied by 1 in this way so that this looks like an integral starting at x. Okay, so this is roughly like epsilon times the integral from x to infinity of 1 on y to the 3/2 e to the minus y on 2 dy, which is about epsilon on x to the half e to the minus x on 2. Okay, so that's I'm not being terribly careful or precise or detailed about that, but all of this is perfectly rigorous, and you can you indeed get a bound which is so order epsilon over x to the half e to the minus x on 2 for x bounded away from 0. Okay, so that's worth keeping in mind. You start to get this exponential penalization for seeing large components on that scale. Okay, and then so the last thing I want to say about branching processes before we move on to random graphs is this branching process duality that I've now mentioned a couple of times. So let me go on to that. So this is a general phenomenon, but I will mention its specific sort of instantiation in the setting of Poisson branching processes as well. So so let's fix an offspring distribution mu and let T be a BNMA mu tree. Okay, and let's let, as usual, Q be the extinction probability. Okay, and I want to ask about what's the probability of extinction conditional on the number of offspring of the root. Okay, so we have the root, and it has some number, k of children. Maybe k is 4, right? And then the probability that so the probability that the tree is finite, that extinction occurs, and that the root has exactly k children. Well, that's, by Bayes, the probability of seeing k children is mu of k. And then if the root has k children, then in order for the tree to be extinct, each of the copies of T rooted at the children of the root, right, by the branching property, each of these looks like an independent BNMA mu tree. Those all have to go extinct as well. Okay, so we get mu of k times q to the k. Okay, and so that means that the probability that the root has k children, given that the tree is finite, again just by Bayes, is mu of k times q to the k minus 1. Okay. But now, writing, TV up arrow for the subtree rooted at V. So this is agreeing with my earlier notation, but now the trees are growing downward, which makes the up arrow a bit funny. But so this is T2 up arrow, for example, right? So so with this notation, then these trees are conditionally given that the whole tree is finite, and given that the root has k children, then these subtrees, again by the branching property, are independent copies of their independent branching processes. But now they're conditioned to be finite as well, because T was conditioned to be finite. Okay, so that says that conditioning the whole tree to be finite, we still have we get, oh, there's a equals k missing here. Sorry. We have a new offspring distribution, but the branching property still goes through, and you see a different BNMA tree. Okay, so in other words, so given it's finite, is, let me call it mu hat. So it's a BNMA mu hat tree. And where this mu hat is the distribution that's just given here. So mu hat of k is mu of k times q to the k minus 1. Okay, so just as a sanity check, if we know which BNMA trees have are almost surely finite, and this one had better be finite because we conditioned it to be finite, right? So this mu here, mu hat, should be a subcritical offspring distribution. It should have mean at most 1. Okay, well, let's check that that's the case. So if x hat is mu hat distributed, then what's its expected value? So that's the sum j at least 0, j mu hat j, which we can write as the sum of over j at least 0, j mu j q to the j minus 1. Okay, but this here, remember that g of s was the sum of mu of s times s to the x, right? So this was the moment generating function of the original offspring distribution. So here we just recognize g prime evaluated at q at the extinction probability. Okay. And that is indeed less than 1. So if we remember the picture, I'm going to just pull it over from the proof of the fundamental theorem of branching processes, right? When we well, less than or equal to 1. So if we started with let's just focus on the case where we started with a supercritical branching process, so the initial mean was greater than 1, then this is what the picture looks like, right? This is the curve g of s. It has slope greater than 1 at 1. It's convex, and so when it crosses the line y equals x at position q, its slope is less than 1. Okay, so this so that's saying this g prime of q is less than 1. And if on the other hand, if mu itself was subcritical, right? If the sum of I mu of I is at most 1, then Q is 1 through this whole argument. So conditioning on being finite hasn't changed anything. We just have our original offspring distribution. Okay. C phi t equals K, G of Q equals Q. I agree about the C phi t equals K. Okay. So in fact, this this mu hat, you can find the moment generating function of mu hat by just zooming in on this quadrant of G mu. Okay, if you take this picture down here and blow it up to live on the interval 0, 1 instead of 0, q, then what you have here is precisely the moment generating function of mu hat. Okay, so so that's a nice way to think about what's happening when you condition to be finite. Okay, so that's the little well, that's what almost everything I wanted to say about Poisson process duality. If you take a supercritical Poisson process or a supercritical branching process, condition it to be finite, you get a subcritical branching process. Now, in the particular case of Poisson branching, like before, you get sort of more explicit and nice asymptotic formulas, or non-asymptotic formulas, just formulas for the parameters of the Poisson process. So if you start with a Poisson lambda branching offspring distribution, then you can work out what the dual offspring distribution is, and it's again a Poisson distribution, but now its parameter is changed as follows. So if you start with lambda, then you end up with 1 minus theta of lambda. Okay, so remember theta of lambda was the probability that Poisson lambda bien-aimé tree was infinite. Okay, so this is really just lambda times the extinction probability. Okay, and this is notation I'll use this lecture and possibly the next one to mean a bien-aimé tree with offspring distribution mu being Poisson lambda. Okay, so that's how. So this this describes how the mean. Well, it's nice that you stay within the parameterized family of Poisson offspring distributions, but moreover, you have quite an explicit formula for how the mean changes when you condition on being finite, right? And if lambda was at most 1, then this theta here is 0, so 1 minus theta is 1, and you're just saying that nothing changes. Okay, so that's the first part, and then I also want to state something about what happens when we're very close to the critical value 1. Okay, so if lambda is 1 plus epsilon, then this dual parameter 1 minus theta lambda is 1 minus epsilon times 1 plus little o1. Sorry, the 1 minus 1 plus little o1 times epsilon. So 1 minus epsilon 1 plus little o1. So that's as epsilon tends to 0. Okay, so so close to 1, you really are effectively just going from Poisson 1 plus epsilon to Poisson 1 minus epsilon when you condition on finiteness. Okay, so there are some other exercises from last lecture about the sort of what asymptotics you can extract from this Poisson survival probability. I'm not going to go through those in detail, but I hope that you will make the time to work that out for yourself. I'm actually going to use this fact. So at a minimum, you should sort of internalize the things I'm mentioning about theta, even if you don't go through every detail of their derivation. Any questions about all that before I switch from branching processes to Erdős-Rényi random graphs? Okay. So So let me do so. So in the polls we ran, the about background. Oh, I just see one question from Yinon. If mu is supercritical, then hat mu is always subcritical, right? Yeah, so that's exactly what we were checking here, because we said that well, in fact, even if mu is subcritical, then mu hat is mu, and if mu is supercritical, then this derivation here told us that mu hat was subcritical. So so yes. Strictly less than 1, indeed, because you have to, because this is a convex. If you start with something strictly supercritical, then when you, and then when this convex function recrosses the line, it has to have slope strictly less than 1. Okay, good. So, so continuing on to Erdős-Renyi random graphs. And I'm going to think about these dynamically right from the outset. So I'll call them Erdős-Renyi processes. Okay, much of what I say will only be about those processes observed at fixed times, but there's no, it's conceptual. It's not conceptually harder to introduce them all at once. So, so these are random subgraphs of the complete graph. So Kn is the complete graph. So that means it has vertex at integers 1 up to n, and n choose 2 edges. Okay, and now they're sort of almost right from the outset. There were 2 versions of the Erdős-Renyi process defined. So one in discrete time, and so for this one, you simply choose a random ordering of the edges and add them in that order. So choose a uniformly random permutation. So E1 up to E, and choose 2 of the edges of Kn. And then, so for m from 0 to n choose 2, we'll let, so G and M have vertices n and edges E1 up to EM. Okay, so you've permuted the edges and you add them one at a time. Okay, so at time 0, you have the empty graph, and at time n choose 2, you have the complete graph. We won't talk very much about the discrete time model, because the continuous time model is easier to think about in various ways, and results from one most results from one can be transferred quite straightforwardly to the other. So you're sort of welcome to think about whichever one you find more appealing for most intents and purposes. So in continuous time, the process is a little bit different. So in this case, instead of ordering the edges at the outset, we're going to weight the edges randomly. So we'll give ourselves a family of random variables UE, which weight the edges of the complete graph. So these are going to be independent and uniform on 0, 1. Okay. And then for P from 0 to 1, we'll define a graph GNP, which has, again, the vertex set is just the integers 1 up to n. And now the edge set is, so just whichever edges of the complete graph have this random weight at most p. Okay, so in this graph, each edge is independently present with probability p. Okay, so you know, if you like, you just toss a biased coin, which has probability P of coming up heads. If it comes up heads, you include the edge of it, and otherwise you don't. Okay. This is a completely, self-indulgent digression, but I just saw this paper of Susan Holmes and Percy Diaconis and a third author I'm forgetting, where they analyzed tossing of real coins, and they, including coins, they had special coins manufactured which had lead on one side, like so that half of the coin was made of lead and the other half was made of balsa wood. And those coins are perfectly fair because angular momentum doesn't care whether the coin is heavier on one side and lighter on the other. It still rotates in the air. But if you spin the coins, obviously, then that matters a lot. Then the balsa wood always comes up on top. And in fact, so American, I forget what currency they were talking about, but maybe it was quarters. If you flip them, they're fair, but if you spin them, then they have a decided bias toward coming up tails. So spinning and flipping coins is not the same, and spinning is actually more biased. Anyway, that's completely unrelated to my course. So let me continue. As I said, I won't say much about the discrete time model. So let me just make a couple of quick remarks connecting the two. By the way, so in the discrete time model, you go from the empty graph to the complete graph as m ranges from 0 to n choose 2. In the continuous time model, this as p increases, more and more edges will have their weight at most p, and so you go from the empty graph to the complete graph as p ranges from 0 to 1. Okay, so here are some connections between the two. So the conditional distribution of GNP, given that the graph has some number m of edges, is just the same as the distribution of GNM. Right? Because the edge weights are exchangeable, so if I tell you that m of them are at most p, which m are at most p is I mean, any m of them are equally likely to be those that have weight at most p. Okay, and so another that's sort of is one connection between the two. That means that we can, if you like, that means that we can get results from GNP from results for GNM by averaging out over m, right? So if we want to go from here to here, if we would be averaging out over the random number of edges. Okay, and on the other hand, if we order the edges of the complete graph, so as E1 up to E and choose 2 in increasing order of weight, so of their UE weight, so that means that UE1 is less than UE2 is less than UE and choose 2. Then this permutation is a uniformly random permutation. Again, by the exchangeability of the edge weights, the order statistics form a uniform permutation. And so that means that if we add the edges, as we increase p from 0 to 1, this is the order in which the edges get added. Okay, but that's just a uniform permutation, like what we did in discrete time. Okay, and so so that says that the graph, if we look at the sequence, if we only observe the continuous time process sort of in a sequence of snapshots at the times when the edges come along, then what we see has precisely the same distribution as the discrete time process evaluated, sort of observed at its sequence of discrete times. Okay. So that's about all I'll say about the discrete time model, unless there are any questions. So my goal for the next couple of lectures is to understand how the component sizes evolve in GNP as P varies. Okay, so there are many kinds of interesting questions you can ask about random graphs. You know, there's thousands or tens of thousands of papers about various properties. When, you know, how many colors does it take to properly color them? For what values of P are they Hamiltonian? For what values of P does every vertex belong to a triangle? For what values of for what value of P does, so, you know, pick your favorite graph property and ask about when that graph property emerges as a function of P. That's one sort of set of kinds of questions. And then there's all sorts of papers about statistical mechanical models on random graphs and interacting particle systems on random graphs. You know, you name it, someone's probably studied it on their Schrödinger graph. But the question, you know, by analogy with what we just saw for branching processes, I'm going to be interested in sort of whether in component sizes. So how big are the pieces of this graph? Okay, so there was I think the very first exercise I set for the class related to the graph GN1/2, and it asks you to show that, because in GN1/2 you see you flip a fair coin for each edge. So each edge is independently present with probability half, and that just gives you the uniform distribution over all labeled graphs with n vertices. And so I asked you to show that the probability that GN1/2 is not connected is 1 plus little o1 n times 2 to the minus n. Okay, so that is to say that the probability, thanks, Joe. The probability that, so this is effectively saying the most likely way for a uniformly random graph to be disconnected is just to have a single isolated vertex. Okay, but this isn't so this is in a sense a question about a fact about component sizes, because it tells you that when you take P equals 1/2, I seem to have changed notation. When you take P equals 1/2, with overwhelmingly high probability, you'll just see a single component of size n and no other components in the graph. Okay, so that's sort of a fairly degenerate kind of answer to the question. I'm going to be more interested in taking values of P where the behavior is a little more subtle and more interesting. Okay, but you know, the spoiler, I guess, is let me say most of the interesting behavior happens around P equals 1/n. Okay, and in this lecture we'll just be focused on upper bounds for P at most 1 plus little o1 over n. Okay, I can't tell if I'm coming through okay. Is it glitching a bit? Yeah, it's okay. Okay, great, thanks. Good. So let me give myself just a little bit of notation before I state my first result. So so given a graph G and some vertex of the graph, I'll write So so n of v or ng of v to be the set of neighbors of v and g. Okay, so this is you know, the set of vertices w such that VW is an edge of the graph. Okay, and more generally, I'll say that NK. So this is the set of neighbors of a vertex. You could also say it's the set of vertices at distance exactly 1 from that vertex in the graph distance. Okay, and so more generally, I'll say NK of V is the set of vertices W such that the distance in G from V to W is equal to K. Okay. And then I'll let the connected component, so C of V or CG of V, so this is the connected component of V in G. Okay, so it has vertices, just everything that's at finite distance from V in the graph. Okay, so that's the union over K at least 0 of NK of V. All right. And so now I'd like to prove, state and prove a first proposition about expected component sizes. So so for any n at least 1, and any p which is at most 1 over n minus 1, and any vertex of the graph, the expected size of the component containing V is at most 1 over 1 minus p n minus 1. Okay. And so the way we'll prove this is by thinking about exploring the graph in stages. So one layer at a time, starting from the vertex, exploring its neighborhood, then exploring its second neighborhood, etc., etc. Okay. So I think that was my last image for today. I can close that. So let's compute. Let's ask about. Let's imagine that we've been exploring revealing the graph layer by layer. Okay, you know what are the neighbors of the vertex V? There in you know, it's important here in GNP. Okay, what are the neighbors of the vertex V? They're you know, all the edges incident to V in this graph are all the edges with weight at most P. So there's some binomial number of neighbors, right? And then I can sort of ask about the value of those random variables one step at a time. First, I'll ask about these ones, and then once I learn about these ones, I'll ask about all of these, all of the edges from n1 of V to the rest of the graph, and so on and so forth. Okay, so I'm imagining that I've been going along doing that. I've reached level k minus 1, and now I'm asking about how many edges I expect from the k minus first neighborhood into the rest of the graph. So that's asking about the size of nk of V given the neighborhoods nj of V for j at most k. Okay. Well, let's think about querying. So for each vertex, one after the other, in some order, we'll ask, okay, well, how many neighbors does the first vertex have in the rest of the graph? Okay, so if I compute this expectation in that way, that's saying that I can sort of sum over all the vertices in NK, well, I guess maybe I want to say it a tiny bit more before I write the sum. You see, if I count, if each of the vertices which is a neighbor of V counts its number of neighbors in the second neighborhood, then I'll get an overestimate of the size of the second neighborhood, right? Because this vertex would count 2, this one would count 1, this one would count 4, but this vertex has been counted twice by both of these vertices, and this one has been counted twice by both of these vertices. Okay, so if I sum up the number of neighbors of each vertex and the rest of the graph, I get an overestimate on the total size of the kth neighborhood, right? So so that means that this is a strict inequality here. Sorry about that. So that means that I can bound this expectation from above by the sum over vertices in the k minus first neighborhood of, so the expected number of new vertices added by neighbors of W. So that's NW minus the union over J at most k minus 1 and J of V, given all these neighborhoods. Okay. Well, what's that? Okay. This, the expected number of neighbors of each vertex in the rest of the graph is exactly the same by the symmetry of the model. Okay, so this is just the size of nk minus 1 of V times, and then for a given vertex in nk minus 1 of V, we have a binomial number of neighbors in the rest of the graph with success probability P. Okay, so that's this. So for each vertex in the rest of the graph, we add an edge with probability P, and the number of such vertices is n minus the size of this union. Okay, and so just for an upper bound, let's say that that's at most the size of nk minus 1 times P times n minus 1. Okay. So now we can, by taking expectations in this inequality to, we want to bound the expected value of nkv, and we only have a conditional expectation right now. So we'll take expectations on both sides, and this gives, the expected size of nkv is at most the expected size of nk minus 1v times p n minus 1. And so by induction, that's at most so p n minus 1 to the k, right? And so, well, we know that the size of the component containing v is just the sum over neighborhoods of the expected size of the kth neighborhood. So that's at most the sum of p n minus 1 to the k, which is 1 over 1 minus p n minus 1. Okay, so that's just an easy recurrence, which gives this this upper bound on the size of the expected size of a component. Okay, any questions about that? Okay, I saw movement, so I assume people are still there. Good. So so let's immediately use that to prove that when we look at the largest component in a random graph, which so we said we were going to study random graphs where p is at most a little bit more than 1 over n. But I'm going to start by actually studying graphs where p is less than 1 over n. So so let's let's fix some constant c in 0, 1, and look at what happens when p is c over n. Okay. Then already from this bound, I can get that in GNP, the size of the largest component is sublinear. Okay, and that's not hard to see from this bound, but it gives me, so it's an easy proof, but it gives me the chance to introduce a tool that I'll use repeatedly. So so I'd like to do that now. Right. So to prove this, I'll use the following easy lemma. So well, let me actually just for sort of here and hereafter, I'm going to use the notation C max for the lexicographically least largest component of GNP. Okay, so what this means is pick this is the connected component with the largest number of vertices, and if there's a tie, pick whichever component has the smallest labeled vertex in it. That's the tie-breaking rule. Okay, so this just means that the tie break is smallest label. Okay. So then the probability that the largest component of GNP has size at least k is at most n over k times the probability that the component containing vertex 1 has size at least k. Okay, so this is just an easy way to transfer information about bounds for the size of one component into bounds on the size of the largest component. Okay, and the heuristic reason that this is true is that conditionally given that, you know, if I tell you there's a component of size at least k, well, because the vertex labels are exchangeable, with probability at least k over n, vertex 1 is in that component, and then vertex 1 will have component size at least k as well. Okay, so that's the sort of the reason why the lemma is true. You know, I'll give you a quick proof as well. So first, let's say that so uniformly permuting the vertex labels doesn't change the distribution of GNP. And so that means that the probability that vertex 1 is in the largest component, given that the largest component has some number j of vertices, is at least j over n. Okay. It might be even bigger because there could be more than one component with maximal size, but it's at least j over n. Okay, and now this left-hand side here is equal to so the probability that 1 is in the largest component and the largest component has size j divided by the probability the largest component has size j. Okay, and now for an upper bound on that, I can just drop the, you know, if 1 is in the largest component and the largest component has size j, then in particular, the component containing 1 has size j. So an upper bound on the top is the probability that the component containing 1 has size j. And then I'll just copy the lower bound over, the denominator over. Okay, and so that says that the probability that C max has size j is at most n over j times the probability that C1 has size j. And now, to get this bound up here, we just sum over k at least j, j at least k. Okay. So does that make sense? Okay. So we have this bound here, and now if we just use Markov's inequality to bound the right-hand side and use our bound on the expected size of C1, we get a useful upper bound in probability on the size of the largest component. So this tells us that, the statement of this and its proof are basically the same. So I'm just going to sort of derive the corollary, and then that will be the proof. So the probability that this C max is at least k. So we said that's at most n over k probability that the component containing 1 has size at least k. And so that's at most by Markov. So n over k times the expected size of C1 divided by k. And now that we said, so this, I guess here I should insist that, so for p at most 1, so what did I need for that bound? P at most 1 over n minus 1, right? And that gave me, so I have n over k squared times 1 over 1 minus n minus 1 p. Okay, and that's, maybe I'll just clean that up and say that that's at most n over k squared 1 minus np. Okay, so that's, so let's now use that bound to prove the theorem. Okay, so remember the theorem said that the largest component with high probability is sublinear when p is c over n for c less than 1. Okay, so there's the theorem, and its proof isn't very hard now, right? We have for positive delta, the probability that C max is bigger than delta n is at most n over delta n squared. That's my n over k squared. And then 1 minus np is just 1 minus c, because p is c over n. Okay. And so that gives me 1 over n times 1 over delta squared 1 minus c, which tends to 0. Okay, and so that's the whole proof of the theorem. So that was really easy. But when you see a proof that straightforward, you usually want to ask yourself how much more you can extract from it, right? I just wanted to give you the simplest, cleanest version of it. So you see the technique. You just right. What was the whole technique that we used? We used a simple recursion to bound the size of the expected size of the component containing a given vertex. Then we used symmetry to say that to relate the size of the largest component to the size of the component containing a specific vertex. And then we just used Markov's inequality basically to get upper bounds on the component size. So that's the whole proof structure. Let's think about what this argument actually says, right? So if we look here, we had a ton, in order to make this tend to 0 here, we had a lot of room. This is tending to 0 very quickly, right? We could have gotten away with something smaller than 1 over n here, right? The same argument. shows that if omega n is some function, there's this is, I'm going to use this notation a lot in the next couple lectures. So some generic function tending to infinity as n tends to infinity. Okay. Then 1 over n to the half. So 1 over root n times omega n times the size of C max tends to in probability to 0 as n tends to infinity. Okay, so because then when I plug in root n omega n in place of delta n, the root n squared cancels the n, and I still have something tending to infinity on the bottom. That's the whole argument. Okay, and just for notation, or this concept, I could, or this fact I could rephrase as saying that so C max is order root n in probability, right? Because this tells me that for any for any epsilon, there's a k such that the probability that C max has size greater than k root n is at most epsilon. Okay, so, or in other words, C max divided by square root n is tight. Okay, so that's one strengthening. We can say it's not just sublinear, but it's at most size square root of n. That's not a terribly sharp bound, by the way. For this range of C, you can do quite a bit better, and I'll either tell you, do that explicitly or leave it in the exercises. It's not very hard. But the largest component size in this range is actually logarithmic, not polynomial. Okay, so that's one way you can strengthen the theorem. Replace this 1 over n by something better. Okay, another way you can strengthen the theorem is by trying to let p get closer to n here, not just constant less than 1 divided by n, but some 1 minus little o1 over n. Okay, so let's do that as well. So let's so use this technique for p being 1 minus little o1 over n. Okay, and specifically, I'll write. So let's fix a function epsilon n tending to 0, and I'll need it to not tend to 0 so fast. So I want n times epsilon n to tend to infinity as n tends to infinity. Okay, and then we'll ask about component sizes in gn 1 minus epsilon over n. Okay, so if I fix any positive delta, then in gn 1 minus epsilon over n, what's the probability? What bound do I get from this argument for the probability that C max has size bigger than delta n? Well, I still get this n over delta n squared. Okay, but now I have 1 over 1 minus np, so that's n 1 minus epsilon n over n. Okay, and so that's 1 over delta squared times 1 over n epsilon n. And now, because I assumed that n epsilon n tends to infinity, this still tends to 0. Okay, so this says that, so in other words, so if p is at most 1 over n minus omega n over n squared, I can write, saying that n epsilon n tends to infinity says that this ratio is something large divided by n squared. Then the size of the largest component converges in probability to 0. Okay, so now it's worth just thinking for a second. This again isn't tight, and we'll do better. For the moment, I'm just showing you the kinds of bounds you can get by following your nose. But it's worth thinking about what an error term like this is doing, right? The complete graph only has n choose 2 or order n squared edges in total. Okay, so this this, when you change p by order 1 over n squared, then you're on average only adding like order 1 edges. Okay, so this is really, if you like, only like barely more than a constant number of edges away from p equals 1 over n. Okay, so that's sort of, we're really getting like as close as you can get to 1 over n without getting something that's literally kind of like no change in the graph. Okay, and you can actually check that for like for p this small, the random fluctuations of the number of edges are much bigger than the fluctuations you get by changing p that much. So really a result that holds for this value of p would also hold for p equals 1 over n. Okay, so so curiously, and in the sense, the main reason I wanted to present this technique to start, aside from the fact that it's really easy, is that in an important special case, it actually gives tight bounds. Okay, so that's the last thing I'll say about this technique before I go on to the sort of case p greater than 1, where we'll see that kind of, well, not two different arguments still yield useful bounds. So an important special case is this is when p has the following form. So it's just a little bit less than 1 over n, but the correction is going to be of order n to the third. Okay, so here c is positive. Okay, so it's an epsilon n, but a particular choice of epsilon n. Okay, so then in that case, well, 1 minus pn is c over n to the third. Okay, and so in GNP, this tells us that the probability now that the largest component has size bigger than some constant a n to the 2/3. You know, I'm using the constants that I know will work out, but it's not hard to figure out what they'll be just by staring at this. You know, this is the sort of upper bound we get, right? N over k squared 1 minus np. So here we get n over a n to the 2/3 squared, and now we said that 1 minus np is c over n to the third. So that gives us n to the third over c. And now all the powers of n cancel. We have n to the 4/3 on the top, n to the 4/3 on the bottom, and so we're getting 1 over ca squared. Okay, and that so that bound tends to 1 as a tends to infinity. Okay, and so that tells us that that the size of the largest component, so for p 1 minus c over n to the third divided by n, the size of the largest component is at most of order n to the 2/3. So this is order n to the 2/3 in probability. Okay, and this turns out to be tight. And I do mean goes to 0 as a goes to infinity. Thank you. Okay, so I can't quite show you that it's tight yet, but it is. It's, you know, once you know that this is the correct order of magnitude, it's sort of striking that you can derive it using such a simple argument. Okay, so to go beyond this, we need additional techniques. So let me just take a sip of water and see if anyone has any questions about this set of techniques. Slides are already online, by the way. Okay, so so I'd like to I'd like to move from p less than 1 over n minus 1 to p at most 1 plus little o1 over n. Okay, so in this case, you know, this bound, the expect that we got, which was the sum of p n minus 1 to the I, or to the k, is useless if we're allowing p bigger than 1 over n minus 1, obviously. So we need to do something else. And we're going to use, the new tool we use is comparison with the branching process. Okay, so so for this, I need to remind you of the notion of stochastic comparison of random variables. So I expect this is familiar. You know, I think it's sort of part of a standard probability course curriculum. So for random variables, x and y, we say that x is stochastically dominated by y. So the notation for that is x is less than or equal with this prec less than or equal y. So this just means that the probability that x is at least t is at most the probability that y is at least t for all real t. Okay, and so equivalently, you know, x is stochastically at most y holds if and only if there's a coupling of these random variables. So coupling x prime, y prime of x and y, such that the probability x prime is at most y prime is equal to 1. Right, so a coupling of them means there's a way to define random variables with the same distributions as x and y, but on the same space, and such that this x is almost surely less than y. Okay, so so now with that notion at hand, I can state the relation between component sizes. So the stochastic relation I'm going to use first for component sizes. So this says that for any, so in fact, the way I'll state it holds for any p between 0 and 1. It will only be useful for certain values of p, but the fact is true for any p. So so c is such that e to the minus c is at most 1 minus p, and in GNP, the size of the connected component containing any vertex v is stochastically at most the size of a certain tree, which is Poisson n minus 1 c bien-aimé tree. Okay, so I think, you know, I gave myself some notation for that, actually. I could write T Poisson n minus 1c. Okay. So is the statement clear? This says that, you know, the component size is stochastically smaller than a certain Poisson branching process. And you can sort of see why this might not be very useful if, like, if C is you sort of want n minus 1c here to be something not too big, right? So C should maybe be like of order 1 over n or something like that, or else you have a branching process that has huge numbers of offspring. Okay. So we'll prove this by induction. So induction on n on the size of the graph. So if n is 1, then it's obvious. Okay, maybe I should say that it's a little bit weird that I can. It might seem a little bit weird that I can prove something like this by induction, but the point is that on the right-hand side. So I'll start by looking at the a bit like in the previous neighborhood exploration. I'll start by looking at the neighbors of the vertex v, and I'll want that that's sort of stochastically smaller than some Poisson random variable. And then in the iteration, if I think about exploring in the rest of the graph, then n has gone down because the rest of the graph has fewer vertices. Okay, so then if I get a stochastic domination with a smaller value of n, that's only better because I've reduced the mean of the Poisson branching process. And so I'll use, I'm saying it now, but I'll use it without comment later, that if I look at the size of a Poisson branching process with some mean lambda, then increasing the mean lambda just stochastically increases the size of the Poisson branching process. Okay, so that's what I'm that's how the proof is going to go. Okay, and so now so if n is bigger than 1, we'll argue by induction. Okay, so first I need so I'm going to build up from Bernoulli random variables. Okay, so here's the key step, if you like. So if B is Bernoulli with success parameter P, and P is a Poisson random variable with mean C, and e to the minus C is at most 1 minus P, then the probability that B is 0, well, that's 1 minus P. That's bigger than e to the minus C, which is the probability that P is 0. Okay, so that says that with these values, with these parameters P and C, the Bernoulli random variable is more likely to be 0. Okay, but the Bernoulli is always at most 1, and if the Poisson random variable isn't 0, then it's at least 1. Okay, and so that so if P is at least 1, then P is at least B, and so that that implies that B is stochastically smaller than P. Okay, so that's sort of where the form of our inequality between P and C comes from, because now if I take B1 up to Bn minus 1 to be independent Bernoulli P random variables, and then let's say P1 up to Pn minus 1 are independent with so Poisson C random variables, right? Then if I take each of these individually is stochastically dominated by its homologue, its counterpart on the right, then summing the independent copies preserves the stochastic domination, right? If you like, because if I can couple so that B1 is at most P1 and B2 is at most P2 and so on, then I just take the product space of all of those couplings, and I have a space where each BI is at most PI, and so the sums also satisfy that inequality. Okay, so this this gives that so B1 plus Bn minus 1 is stochastically at most P1 plus Pn minus 1, and this is Bernoulli, and this is rather binomial n minus 1p, and this is Poisson n minus 1c. Okay, and so this this gives that well, this is the distribution. On the left, we have the distribution of the neighborhood of V in the random graph, and So that's at most a Poisson stochastically. Okay, so now that's the sort of key step for the induction. So now we'll write the neighborhood as v1 up to vk. K is some random value, and then for I from 1 to k, I'll let ci be the component containing vi in the graph. So GNP, where I remove v, and I also remove the components c1 up to ci minus 1. Okay, so maybe a picture of that is in order. Right, so here's the vertex v. Here its neighbors v1, v2, vk. Here's the rest of the graph. And now, so c1, the component containing v1 over here, this is c1. And then, so c2 is the component containing v2 over here. So we're not allowed to use any of this component. Okay, so so each of these, you figure out what the component is, you take it away, and then you look at the connected component in whatever's left for the next vertex. Okay, so then by induction, conditional on the neighbor, the set of neighbors, and on c1 up to ci minus 1, then we know that so ci just looks like the component containing vi in a graph G and P, but for a different value of n. Okay, so ci is stochastically smaller than so the size of a Poisson bien-aimé tree, whose parameter now I'll call ni, so ni minus 1 c. Okay, and this is just n minus 1 minus the size of all those previous components. It's all the things you had that you took away and you weren't allowed to use when you were exploring the ith component. Right. So this is just n minus 1 for v1, and then it's n minus 1 minus c1 for v2, and so on. Okay. But now, by the comment I made at the start, this ni is at most n, and so this the size of this tree is stochastically at most the size of a Poisson bien-aimé tree with parameter n minus 1c. Okay, and it's important that that's true even after I condition on all this information. Okay, so because that's true even after conditioning, that tells me that the size of CV is, so that is exactly 1 plus the sum from 1 up to k, which was the size of NV of CI, right? That's the component containing V just contains V plus all of these pieces. And that's now stochastically at most 1 plus the sum I from 1 up to NV of the size of TI, where these are now, because we had this stochastic bound even conditionally, we can say that on the right here, these are independent with distribution. So Poisson n minus 1c bien-aimé trees. Okay. But what's this? This is, so we're saying 1 plus, last step, sorry. We also said that NV was stochastically dominated by a Poisson n minus 1c random variable. So this whole thing is stochastically at most 1 plus sum I from 1 to a Poisson n minus 1 C of the size of Ti. Okay. Is NV excluded from the definition of cal C1? Yes, I should have done that. Yes, thanks. So yeah, I could have excluded so V1 up to VK taken in here. I think it would have made sense to also exclude V1 up to well, maybe V I plus 1 up to VK. I don't want to exclude V1 from its own component, so I'd better start at V2. Yeah, but I think it probably, yeah, I think that probably fixes it. Okay, but now, so the point is, sorry for maybe that wasn't the best moment for me to answer a question, even though it was a good question, just because I hope everyone is still sort of sticking with the flow. We've showed that the size of this component is stochastically dominated by 1 plus the sum of a Poisson number of Poisson trees. Okay, but 1 plus, if we look at the size of a Poisson tree, that is 1 for the root plus a Poisson number of Poisson trees, which are just the trees, the subtrees rooted at the children. Okay, so this expression on the right here is exactly just, you know, by doing a sort of one-step recursion on a branching process. This is the same as the law of a Poisson n minus 1 C bien aimé tree. Okay, so that's sort of the whole proof. Okay, and what's sort of cool? Okay, so the proof is not too bad. I think it's as tight as you can hope for in terms of an exact coupling, because you sort of, you have to have the Bernoullis right, or else it isn't going to work, and then that already gives you the whole structure. Okay, what sort of I think it's fair to say surprising is that this is useful. This coupling is useful even when this Poisson parameter here is bigger than 1. And you might think that it's useless when the Poisson parameter is bigger than 1, because then the tree on the right might be infinite. And so infinity is not a really useful upper bound on something that lives in a finite graph. But the point is that because we have control on the probability it's infinite, we can still extract quantitative information about probabilities of given sizes for CV from that bound. Okay, so maybe I'll just, since there's only 5 minutes left, I don't think I'll try to do a proof of such a bound. I'll leave it for next lecture. But what I will do is sort of state a corollary of this, which makes sort of the values a little bit more explicit, and then state the proposition which gives the bound I'd like to prove at the start of next lecture, and then we'll call it a day. Okay, so just this is really just from sort of plugging in values to the bound we just proved in the theorem. So if n minus 1p over 1 minus p is less than lambda, then in GNP, the size of the component containing V is stochastically at most the size of a Poisson lambda bien aimé tree. Okay, and so this is just because to prove this, you just use that 1 minus p is at least e to the minus p over 1 minus p for p between 0 and 1, which is easy to prove from a Taylor expansion. And so that means that 1 minus p is at least, you just rearranging this, then p over 1 minus p is lambda over n minus 1, right? So that says that 1 minus p is at least e to the minus lambda over n minus 1. Okay, so so now if we call this value up here c, then the theorem tells us that the size of the component containing v is stochastically at most the size of a Poisson n minus 1 c in a matrix. And it feels a bit like I'm going in circles, but c times n minus 1 is just lambda. So that's this. Okay, so that's really just a direct, almost just a rewriting of the proposition with different names for the terms. And so now I'll close with the proposition I'd like to prove. I thought I'd get to today, but I didn't. If we fix any sequence epsilon n, which is non-negative, so we want to get a probability, so 1 plus epsilon over n should be at most 1. Though I'm thinking of epsilon as small, but I don't actually need it for the theorem, so or for the proposition. And I'll let p be 1 plus epsilon over n. Okay, then in GNP, I'm going to get bounds on the probability that the largest component has size bigger than s. So that probability is at most, so 2 plus little o 1 epsilon n over s plus order 1 times n over s to the 3 halves. Okay, and the proof of this isn't long, but I'm not going to try to fit it into 2 minutes. I'll just say basically what's happening is that the coupling tells us that one of two things should happen if this size is going to be large. Either this tree was infinite or it was finite but large. Okay, and then what? So this term on the right corresponds to this tree, which gives us an upper bound being infinite, and this term corresponds to it being finite but large. And the way we bound that is because we know that once you tell me the tree is finite, then the duality result tells me it looks like a subcritical tree rather than a so a branching process with mean less than 1 rather than mean bigger than 1. And so then I can get effective bounds out of that. Okay, and then we'll use the lemma, which lets us pass information from information about a single component to information about the largest component. Okay, so that's how the proof of that proposition is going to go. I have a couple of exercises. I'm a little bit behind on note writing and stuff. My Wednesday was mostly taken up with preparing my handwritten notes rather than exercises and things. But I suspect you already have a decent amount to think about, particularly if you also think about the exercises I gave kind of over the course of the lecture, and the slides are online with those exercises in. But if I, you might check the website in a half an hour or so, because I might have posted 1 or 2 more exercises if you're looking for things to do. Should the denominator of the first term be n? Okay, let me call it there and then try to answer questions without being recorded.